I will start with the second part of my lecture series. Before I start, I want to apologize if there's too much noise in the background. And there's some gardening going on in the background. If it gets too loud, please let me know. Okay, so fluid structure interaction. Last time, let me just, I'm not going to start from the beginning, don't worry, but let me just fill you in on where we are or where we arrived at in the last talk. So I'm looking at the interaction between a viscous fluid and an elastic structure. And the two pictures you see here are the two models that I'm examining in my lecture. So the first picture, you see an elastic container. This is omega E. And inside this container, we have a viscous fluid. So it's a container with elastic walls, really. Okay, if we apply a force to the fluid or to the elastic body, obviously we will have a motion. The fluid will flow and the elastic structure will deform. And the goal is to find the resulting deformation together with the resulting flow of the fluid. So this is the main problem in my fluid interaction problem. Okay, so last week I talked about the first model. Today I will talk about the model below, but I did not finish my investigation of the first model. So how far did I get? So now we'll have to do a lot of this clicking forward. So the first thing I did was I looked at the physical background of the equations governing the motion of both the fluid and the elastic material, and we arrived at, and I will be there in a moment, we arrived at the the equations of motion of our fluid structure system. Yes, here we are. So to govern the motion of the fluid, we consider the Navier-Stokes equation, or we use the Navier-Stokes equation to describe the motion of the fluid part. And here in this slide, you see in the big system of equations, the first two equations. Those are the Navier-Stokes equations. We have the first equation expresses the conservation of mass. No, the first equation is conservation of linear momentum, and the second equation is conservation of mass in our viscous fluid. Those are the so-called Navier-Stokes equations. The third equation is a coupling condition on the interface between the fluid and the body, stating that the velocity of the fluid, of a fluid particle on the fluid structure surface is equal to the velocity of the surface particle on that interface. So this is simply what we call the no-slip boundary condition. So the fluid particle adhere to the boundary. Classical no-slip boundary condition. So with this boundary condition, we have a classical Navier-Stokes equation in the first three equations. And the last three equations you see in this system here, those are the equations governing the motion of the elastic structure. Maybe I should just point out that the unknown in the fluid equation is the Eulerian velocity field V of the fluid and the scalar pressure field P. Now the unknown in the elasticity equation, the last three equation, is the displacement vector field U, which at any point in the elastic structure tells you the displacement with respect to some reference configuration. The reference configuration you see to the left. Wait a minute. To the right. Sorry. Let me just see if I can set up my pen so I can write. No. No. Just a second. I don't know why I cannot write on the screen.
So, excuse me. So,
yes.
Yeah, you have a TFV VP. Okay. I see. Okay, thank you.
Okay, I'm just fighting some technical problems here. I want to highlight stuff on my screen. I have to press some button here. Yes. Do you see when I'm writing on the screen?
Yes, it is clear.
Perfect. Okay. So, so let me highlight here the. Oh, now again, I pressed something I should not have pressed. Sorry about that. Here. Yeah. So you see here what I refer to as the reference configuration of the elastic structure. Oops, sorry. So here we have the picture of the elastic structure. The domain of the elastic structure is denoted by omega E. Of course, this domain changes in time, so it depends on T. Of course, as the elastic structure changes in time, the domain changes in time, so does the domain omega F of the fluid. So these domains are time dependent. Now, when we express the equations of motion of the elastic structure, we do so in so-called Lagrangian coordinates. That is, we write the equations as equations with respect to an unknown displacement vector field, that is our U, which tells us this the displacement of each point in a reference configuration at time t. So the elasticity equations are written, well, in this reference configuration, which I take, which is or normally do, you take to be the configuration at time 0. So this is omega E of 0. That's why you see the omega E of 0 here. So the elasticity equations, the last three equations written in Lagrangian coordinates, we have conservation of linear momentum. Then we have the cobbling condition. So here you have conservation of linear momentum. Then we have the cobbling condition on the boundary, stating that the force, that we have a balance of forces between the elastic structure and the viscous fluid. And at the outer boundary of our container, the elastic material is clamped to the outer boundary. So on the outer boundary, the displacement is 0. Okay, so that's our equations of motion. I should mention that the Navier-Stokes equations are equations of motion for the fluid. They are written in the current configuration in so-called Eulerian coordinates. And this is the natural way we derive these equations. So elasticity equations are naturally derived in Lagrangian coordinates, and Navier-Stokes equations are naturally derived in Eulerian coordinates. And this gives us, when we couple these equations, of course, well, the system you see here with one set of equations written in the current configuration at time t, or written with respect to unknowns defined in the current configuration and times t, and other equations written with respect to a reference configuration, which we take to be the configuration at time t. Okay, so this we derived these equations last week, and now we're looking at solving these equations. So we're asking the question, if we prescribe some forces, capital F, force in the fluid, and F B ref, this is a body force in the elastic material, so we prescribe outer forces. What is the resulting motion? What is the solution to the corresponding equations of motion? So we are looking for a solution VPU. So V a vector field, P a scalar field, and U our displacement vector field. Okay. Yeah, so we are now trying to solve this this system. So last week I started looking at steady state solutions. So we now look for, if you like, equilibria of our system, so time independent solutions to our equations of motion. That is, we are looking for solutions, meaning a U, a V, and a P, to the system that you see here. And this is just the stationary system corresponding to the system on the previous slide. So we have here equations of a motion with now, of course, a time independent force. I didn't write this explicitly, but that goes without saying when we're looking for steady states. And we look at time independent forces and look for corresponding time independent solutions to our system of equations. Okay. The reference configuration is the same as before. The current configuration, it's still an unknown, but it doesn't depend on time anymore. So we still have the problem here in the steady state case that our that the current configuration, the domain for the fluid equation, is an unknown. But of course, once we know the displacement vector field of the elastic material, when this displacement vector field tells us the deformation, and but of course it's coupled, so that's how it is. Okay, so we're looking for steady state solutions. Sorry, I just have to mute my phone. Problem with online lectures. So yeah, we're looking for steady states, and we do, and we try to find the steady states in the usual manner. When we have, of course, a nonlinear, highly nonlinear problem. So what do? We linearize the problem and look at finding a solution as a fixed point of the problem you see here. So after linearizing, we obtain a linear operator, which we can put on the left-hand side here, and we put all the nonlinear terms that we get on the right-hand side, and define a nonlinear mapping N. And then if we can invert our linear operator L, well, then we can identify a solution as a fixed point of the mapping you see here on the right-hand side, this equation here. And this is the classical way, of course, of finding a solution to nonlinear problem. Okay, in order to obtain such a fixed point, well, we need a framework of Banach spaces. And this framework has to be such that the linear operator acts as a homeomorphism, so that we can invert it in this framework. Okay, so the framework that I choose is the classical LP framework. So in order to show that my linear operator in such an LP framework of LP Sobolev spaces is invertible, I need so-called LP estimates. And for my elliptic systems, it turns out that when I linearize my nonlinear system, which is of course a coupled system, and each of the two component systems in this coupled systems in the steady state case are both elliptic systems. So I'm coupling two elliptic systems. Okay, so in order to get LP estimates, I apply Ekman-Douglas-Nirenberg theory. This is for when you look at elliptic systems, the theory of Ekman-Douglas-Nirenberg is comprehensive. So basically, for any elliptic system, the Ekman-Douglas-Nirenberg gives you estimates. Now, I say for any elliptic system, what is an elliptic system? Well, ellipticity has to be defined, and we spent some time defining what it means to be elliptic in the sense of Ekman-Douglas-Nirenberg, so that we get the LP estimates, and this is quite tedious. You have to introduce weights in order to define the principal part of your symbol, and then okay, then after you find the weights, you can formulate the framework at least, and then you can and then you have to verify that your operator satisfies certain conditions. So ellipticity, properness, complementing boundary condition have to be satisfied. In this case, your system is elliptic in the sense of Ekman-Douglas-Nirenberg, and you get the LP estimates. Okay, so I spent some time doing checking for the linearized elasticity system that this system, the so-called Lemmy system, is elliptic in the sense of Ekman-Douglas-Nirenberg, so that we, for the Lemmy system, get these nice LP estimates that we need. Okay, so I needed to do this. I utilized a very nice theorem of Gemuna, which states that Ekman-Douglas-Nirenberg ellipticity is essentially equivalent to the operator being Fredholm. And the theorem of Gemuna states that if your operator is Fredholm for one Q, the Q should really be a P here for one P. If I just go back to our setting of Sobolev spaces, oh no, here's also a Q. I apologize. So the parameter here everywhere, Sobolev space, the integrability exponent is denoted by Q. So the theorem of Gemuna states that if your operator is Fredholm in such a Sobolev space setting for one Q between 1 and infinity, then it's Fredholm for all the Qs, and the Fredholm index and the kernel stay independent. Okay, so I used this theorem last week. I'll use it again today. Okay, so so we went through Ekman-Douglas-Nirenberg ellipticity also for systems where you have two disjoint boundaries, and then we applied this theory, as I said, to the Lemmy system, which is the linearization of the elasticity equations, our nonlinear elasticity equations. The nonlinear elasticity equations are based on, or we obtain the nonlinear elasticity equations from the Saint-Venant-Kirchhoff model. The stress tensor is called the Saint-Venant-Kirchhoff stress tensor in the nonlinear elasticity system, and after linearizing, we obtain a linearized version of this Saint-Venant-Kirchhoff stress tensor, and this linear version, this is the Lemmy stress tensor, and here you see the corresponding linearized elasticity equation, the so-called Lemmy system down here. Okay, so the Lemmy system, you will not find in literature any good proofs that this system is elliptic in the sense of Ekman-Douglas-Nirenberg, which we need in order to get the LP estimate. So I spent a little bit of time last week to show you how to actually establish this. And I did this by Well, first, of course, verifying that we we have the that the Lemmy system fits into the framework of an Ackermann-Douglas-Nuremberg system with the weights and the corresponding symbols. So we did that, chose the weights, and then I showed that by connecting my Lemmy system to a much simpler Dirichlet system in the component of Fredholm operators in the space of bounded operators in this Sobolev space framework here. I showed that I can connect the Lemmy system to a much simpler system in the component of Fredholm operators, and this connection, this path between the two operators, essentially, is useful because the index is homeotopic. The Fredholm index is homeotopically invariant on such a path. So when you have such a path, the index doesn't change. So I derive that my Lemmy operator is Fredholm of index 0 by by looking at a much simpler system and then connecting my Lemmy system. Here's the simpler Dirichlet system that was my starting point, and I connected this to the Lemmy operator and obtained that my Lemmy operator is Fredholm of index 0. Okay, so this was quite useful. We could use we need the Ackermann-Douglas-Nuremberg theorem to do that, and we end up with the statement that you see here, that the Lemmy operator is a homeomorphism in the corresponding setting of Sobolev spaces. Now we first have that first I showed that it's Fredholm of index 0, and then I showed the kernel is trivial, so it's in homeomorphism, and we ended up with this theorem here. Now, of course, if it's a homeomorphism, if it's Fredholm of index 0 for one Q, I showed it for Q equals to 2, which is the easy case, and then the Game-Owner theorem gives me that it's Fredholm of index 0 for all exponents Q. So the Q is the integrability exponent here in my Sobolev space framework. Okay. So now we have that the Lemmy operator is a homeomorphism in the setting of LQ Sobolev spaces for any LQ. This will be important later because we need to choose a high Q, which I will address today why we need that. Okay, so today I want to talk about well, let me just I have different things I want to talk about. I need to, of course, couple my Lemmy system with my Stokes system. Then I have my coupled linearized fluid structure system. And if I can show that this coupled system is a homeomorphism in the appropriate setting of Sobolev spaces, well, then I can hope to obtain a solution to the nonlinear problem via fixed point iteration. Okay, so we still need that the Stokes system also enjoys a similar homeomorphism property as the Lemmy operator. Now, the Stokes system is if you look into literature, you can find a lot of books on the Stokes system, and certainly a lot of the books on the Stokes system will tell you how to derive or how to establish a good L2 theory, and this is good enough for me, because once I have a good L2 theory, if I can show that my Stokes operator is Fredholm index 0 in the L2 setting, well, the theorem of Ackermann-Douglas-Nuremberg will give me that it's Fredholm of index 0 in any LQ setting. Okay, so let's start by putting our Stokes system into an operator form. So we now have our Stokes operator, put into operator form with some AS operator and a boundary operator. Here you have the symbol of the differential operator, or the system, the matrix that constitute my differential operator in the Stokes system. I have, of course, the unknown in my Stokes system is the vector field V and the scalar field P. So I have 4 unknowns, right? So I have my matrix will be a 4 by 4 matrix. Okay. Yeah, and you have here the last column here is the looks like this, because well, this is the differential. This is the differential operator of the pressure, right? So we have a gradient of P here in our Stokes system, and so that corresponds. So the gradient corresponds of P corresponds to this last column here in my symbol. Okay, so that was just so that you familiarize yourself with the system. And of course, here on the diagonal we have the Laplacian of V here, and on the last line here we have the symbol corresponding to the divergence of V. Okay, so my main symbol of the Stokes systems look like this, AS. And of course, the boundary symbol is quite easy. We have Dirichlet boundary values for the V, not for the P, right? Only for the V, we have Dirichlet boundary values. So our boundary operator looks like this. So I have one column. The last column is 0 because I don't have any boundary values for the P. And then the first 3 columns correspond to the identity matrix to describe my Dirichlet boundary condition. Okay, so this is the Stokes system in this operator form with the corresponding symbols. Okay, I want to put my Stokes systems into the framework of the Akman-Douglas-Nirenberg theorem, so that I can use the Akman-Douglas-Nirenberg theorem, or more specifically the Gemona theorem, which is quite nice. So I have to well, choose weights, and well, I choose the weights like this. So the weights you can choose, there's not a unique way to choose the weights. The weights really tell you what is the principal part, the highest order derivatives in your system. Now, the Stokes system is what you call a mixed order system, because the component of the V vector field in the Stokes system obviously appear with highest order derivative to the order 2, right? The highest order derivatives of the components of the V velocity fields are well 2, because I have the Laplacian of V. But the highest order derivative of the pressure field is 1, right? So but this is not a problem in the framework of Akman-Douglas-Nirenberg system. We can have this mixed order type system by choosing the weights correspondingly. And if you remember, the S and the T weights have to be chosen such that SI plus TI is equal to the derivative order of derivative at the ij position in the symbol. So here we need SI plus TA equals to 2, 2, 2, 1, 1, 1, 1, 1, 1, right? And so, well, if you choose your S and T's like this, you will get exactly that. And of course, also the boundary values have to, or we have to choose weights also for the boundary operator in order to to capture the highest order term, the principal part also of the boundary operators. Of course, my boundary operator here is quite simple. If I add the t and the r's, so here the 2 and the -2, I should get the order of the first column and first line, first column here in my boundary symbol, which is 1. And of course, here also these two give me a 1, and these two give me a 0, of course, because I have 0 order, and then the t for 1 plus the -2 is a -1, but that's not a problem because the negative weights we need that the maximum of the sum of the t's and the r's has to be equal to, in this case, the maximum of the sum of the t and the a's and 0 has to be equal to 0, which is also the case here. Okay, so I don't want to bore you with the choice of weights of the Stokes system. This is an admissible choice. Okay, so the principal part of the Stokes operator actually corresponds to the Stokes operator. We don't have any, after choosing the weights like this, well, we don't have any lower order terms in our symbol. So we have the principal part with symbol characteristic polynomial is of degree 3, and we can check that this corresponds to the number of boundary values that we need in order to be admissible or to conform to the Agman-Douglas-Nierenberg setup. Okay, so our Stokes operator in this Sobolev space setting here is admissible as an operator, as an Agman-Douglas-Nierenberg operator. By admissible, it just means that it satisfies the requirements for the framework. I do not say anything about the operator being elliptic in the sense of Agman-Douglas-Nierenberg. It is elliptic. I can use the Agman-Douglas-Nierenberg theory for the Stokes operator, just as I did for the Lemmy operator. Okay, and this is shown in the following way. Well, first, I can rely almost entirely on say well-known L2 theory for the Stokes system. Existence of a weak solution. This is what you do with with the classical Lax-Milgram theorem. Right, classical application of the Lax-Milgram theorem to the idea when you show weak solutions to the Stokes system, you introduce this space of divergence free of the subspace of your B1p Sobolev space of divergence-free vector field, your Helmholtz decomposition, and thereby you obtain a formulation of the Stokes system where the pressure does not appear. Of course, you have to, once you find weak solution to this reduced system, then you have to construct the pressure, but this you can do. So okay, so this is a standard, just standard weak theory for the Stokes system. We can obtain a weak solution. In divergence free in the Sobolev space V1p. Okay. Here, this 0 here on top means vector field which vanishes on the boundary. So we start with homogeneous boundary values. Okay, so you can show with Lax-Milgram existence of a weak solution. Of course, we need fully we need to have a comprehensive L2 theory for the fully inhomogeneous Stokes system. So we need to the approach is to lift your your right-hand side, your inhomogeneous right-hand side. In our case, this was G. If I just go back to my Stokes system here, my right-hand side is F, G, and H, right? And well, when we have G, when we have in the homogeneous, well, in the case of homogeneous divergence, G equals 0 and homogeneous boundary values, well, we have a solution. And then going to the inhomogeneous case, well, you need to be able to lift your right-hand side in the inhomogeneous case, and thereby reducing the inhomogeneous case to the homogeneous case. So in order to lift the G on the right-hand side in the divergence equation, you need the so-called Bogovsky theorem, which states that if your G satisfies a natural compatibility condition, well, then you can find a vector field capital G with the correct boundary values, homogeneous boundary values, such that divergence of capital G is equal to small g. And so we can use this capital G to lift the inhomogeneous right-hand side of the divergence equation. Okay, so we can also lift the boundary values. That is more standard. Then we need to construct a pressure field, and this we do by exploiting the duality between the gradient operator and the divergence operator. And okay, so I don't want to go into the details of the Stokes system, because this is just want to just show you that I'm using basic weak theory for the Stokes problem that you can find in any book, the book of Paolo Galli, or the book of Hermann Sohr, and other books and lecture notes. So this is quite standard. Okay, so here the theorem that I claim to be a standard theorem on the Stokes system. So for any right-hand side F, G, and H in the subleth, in this framework of subleth spaces in which we are working. So this is the weak theorem of weak solutions. So the right-hand side F is, you can take from this the dual space, and the G just from L2, and the H, the boundary values from the trace from V, the trace space that you see here. Okay, so the data has to satisfy a compatibility condition, and in this case, there exists a unique solution. This is still it's not what we call a weak solution, because in the weak solution there's no pressure, but it's a distributional solution. I even write it here, right? Okay, so if I on my road towards LP theory for the Stokes problem, I have to show that the Stokes operator is Fredholm of index 0 in a strong solution, meaning in the subleth space V22. But my distributional solution here in V12 is a starting point. Now, you can show higher order regularity for the Stokes system. So if your boundary is sufficiently smooth, then with more or less a standard estimates of the difference quotients, and of course some additional technique, you can show higher order regularity of your distributional solution, so that as a matter of fact I obtain with the standard regularity theory and the standard existence theory for weak solutions, and my ability to construct a pressure, I actually show that for any data in this space here, so F in L2, G in V12, and the boundary value H in V3 half 2, trace space on the boundary. For any data in this space, the corresponding weak solution, in fact, is a strong solution in the space V22, V12. Okay, so I can show that my Stokes operator is onto, so the codimension is 0, and I can also show that the kernel is trivial, so that the Fredholm index is 0. So my Stokes operator in this framework here is Fredholm of index 0, and the framework and I emphasize this we show in the L2 setting, right? So where the exponent or the integrability exponent here is 2. So, but the theorem of Gemona says, well, if it's Fredholm of index 0, well, for p equal to 2, then it's Fredholm of index 0 for any p between 1 and infinity. So by the theorem of Gemona, which is really a corollary to the Agman-Douglas-Nirenberg theorem, we get the LP theory that we need also for the Stokes operator. Now, I said that the index is 0. This can't be because the pressure is not unique, right? So the kernel is of course the pressure is not unique. So the kernel of the Stokes operator, the pressure, the kernel is not trivial. It's one-dimensional because of the whenever you have a solution to the Stokes problem, well, you can add a constant to the pressure, you still have a solution. So the kernels is in fact one-dimensional, and also the it's not onto, because in my theorem here my data has to satisfy compatibility condition. So in fact it's not onto. I can in fact the codimension is 1. Actually, I think I did this good. So sorry about the noise. I don't want to make a break before, because I haven't really got started, but on the other hand, I can't hear a thing, and probably you can't either. Okay, so now he stopped. Okay, so let me then speak a little bit. Okay, he stopped. Good. Okay, so our Stokes problem. Well, we have to check that it's Fredholm of index 0, but in order to lift our boundary values, or in order to lift with the Bogovsky lemma on the right-hand side. Okay, in order to lift the right-hand side using the Bogovsky lemma, we need compatibility condition of our right-hand side. So if you prescribe data F, G, and H and look for a solution to the Stokes problem, well, then you have to you get a solution only if these compatibility conditions are satisfied. So this means that the image of the Stokes operator, yeah, perfect. Okay, so now he just said that he's finished, so I can think straight now. Okay, so here we have the the image of the Stokes operator. You see here due to the compatibility condition of the right-hand side. Okay, so this means that we can write the or we can decompose our space for the data into a direct sum of the image, and then a span of at this constant vector here, which is the complement, right, of now I have to formulate it correctly. So you take this vector here, right? So any vector which is orthogonal, so any vector FGH which is orthogonal, we are in a Hilbert space setting here, right? Because the P is equal to 2, so any FGH vector which is orthogonal in the sense to this yellow vector here, well, this will be a vector satisfying this compatibility condition. So the image of the Stokes operator is just the orthogonal complement to the span of this constant vector. But this means that the codimension of our Stokes operator is 1, right? And the kernel, well, the kernel is standard to show that a solution to the Stokes problem is unique up to addition of a constant to the pressure. So the kernel will also be one-dimensional. So the Freitraum index, this is the codimension minus the kernel. It's the dimension of the codimension minus the dimension of the kernel. So we get Freitraum of index 0, but of course, neither the image nor the kernel are actually trivial. Okay, so we conclude that the Stokes system is a homeomorphism in the setting between the x and the y spaces as defined here. Note that in order to claim that the Stokes operator is homeomorphism, I have to factor out the kernel in to construct the x space, and of course the y space. This is the image that we just looked at before. Okay, so now we have, using Agma-Douglas-Nuremberg theory, that the Lemmy operator is a homeomorphism in an appropriate Sobolev space setting, and in the same Sobolev space setting, we also have a similar homeomorphism property of the Stokes system. So now we can go on to the cobbling of the two systems, cobbling of Lemmy and Stokes. Here again, we have our fluid structure domain. We start out here with considering the reference configuration, which has to be, this we also learned last week, has to be stress-free configuration. So just assume that there are no forces acting on your fluid structure system here, then you have, well, some stress-free configuration, which we take to be the reference configuration. Okay, so omega F, omega E, those are the reference configuration domains. Now we introduce body forces on the fluid and the elastic material, time independent, and look for a steady state solution. This means a steady state deformation of the elastic material and a corresponding steady state fluid motion. Of course, here the fluid motion in Eulerian coordinates functions with defined on the unknown, on the deformed fluid domain. Okay, so here we have the equations of motion. This again are the nonlinear equations of motion. Now, actually, I've been missing one important equation, or one important condition, the volume condition. Now, the volume condition, let me see. I mean, the volume condition obviously is a natural condition. We have that the fluid is incompressible, so the volume of the fluid domain remains unchanged at all times. So the volume of the deformed fluid domain here, the steady state deformed, unknown deformed fluid domain, has to be equal to the volume of the reference domain. So this is a volume condition which is derived very naturally. There's no magic about this condition. From a physical point of view, obviously it has to hold. Why do we need it in our system of mathematical equations? Well, the volume condition is is needed in order to obtain a unique solution, because again, the pressure in the Stokes, in the Navier, in the linearized case, in the Stokes, no, this is the nonlinear case. The pressure is only determined up to addition of a constant. So this non-uniqueness is a problem when you do the coupling. So you need to somehow be able to determine the pressure uniquely, and for this you need a volume condition. So I mean, most people will start without the volume condition, and then will find out when they do the coupling, okay, I don't have enough equations in order to determine a unique solution. So what additional physical equations can I add? Well, the volume condition, and then everything works. Okay, so let me just recapitulate here what we're looking at. We're looking at conservation of linear momentum in the elastic material, conservation of linear momentum in the liquid, conservation of mass in the liquid. We have the no-slip boundary condition. On the fluid structure interface, we have the balance of forces on the fluid structure interface, and now also we have a volume condition. Okay, so those are the physical equations which we take to be our model for our fluid structure interaction. Okay, so we know that I have the homeomorphism property of the Lemmy operator. I have the homeomorphism of the Stokes operator, both in the same LP sublift space setting. So how do I now solve the coupled system? Well, first I need to reformulate, if I go back here, reformulate the fluid equations, which are written in the unknown domain. I have to reformulate them in the reference domain. Okay, so the Elasticity equations, Lagrangian description are already written with respect to reference domain coordinates, but this fluid equations are not. So I need a mapping now which maps my fluid domain, current configuration fluid domain, the unknown deformed fluid domain, maps it back or maps it to the reference fluid domain. And this mapping I have to construct. Of course, I have, if I construct it with the help of the displacement vector field of the elastic material, which is my U. The U you see here. The U is the displacement of the elastic material. And now, sorry, is this? There is a funny sound which distracts me, but okay, I will continue. So the operator here, calligraphic F, is an operator which corresponding to a displacement vector field U of the elastic material gives you a mapping of the deformed fluid configuration into the into a reference configuration. Now, the reference configuration of the fluid domain is of course the complement of the reference elasticity domain. Right. So I have here, I can write again. Yeah. So, okay, so given a displacement vector field U, I claim here that I can construct a mapping calligraphic F of U, which when I use it as a displacement vector field, meaning that when I add the identity to this F of U, then I get a deformation here denoted by chi of U, which maps the reference fluid configuration into the unknown deformed fluid domain, which of course is an unknown. Of course, U is also an unknown, but in terms of U, at least I can describe this mapping, which takes my deformed fluid domain into a reference domain. Okay, so this mapping, I can control the determinant of the gradient of chi. It's bounded from below, which is also important. Of course, if U is small, if the displacement U is small, my chi of U is going to be close to the identity. So that's important because at the end of the day, I will be using here the fixed point argument. So I need I need smallness assumption and in this case, well, my U will be small, so my chi of U will be close to identity, which also gives me the bound on the determinant. Okay, so how do you construct such an operator? Well, it's simply just an extension operator, classical extension operator that you obtain from Sobolev space theory. Whenever you have a Sobolev space V2p of E here, so our displacement vector field U, of course, belongs to this space. Well, classical Sobolev space theory tells you that there is an extension operator which extends any U function in the Sobolev space to a V2p function on the whole of R3, and then you can use appropriate cutoff of this extended function to the whole of our 3 to get exactly what you want here. But this is a nice trick actually. So you just, in order to obtain the deformation mapping of your fluid domain, you simply use Sobolev extension of the displacement vector field that is the solution to your elasticity equation. Nothing more, nothing less. And of course, now here we need, however, to choose a p very large, or at least larger than 3 in our framework of Sobolev spaces, in order at least for this deformation to be C1. And of course, the deformation chi of U has to be C1 because otherwise our we would not have a smooth enough domain in order to formulate even the fluid equations in the current configuration. Okay, so we have a displacement vector field once we solve the elasticity equation. Every time we have a displacement vector field, I also introduce the corresponding deformation phi. We did that last week as well. Okay, so now that I have my chi of U, I can introduce the velocity field and pressure in the reference configuration. So corresponding to a velocity field V and P, those of course are still unknowns, but still for every V and P, a vector field pressure functions on the current configuration I can construct just by composition with chi of U corresponding velocity field and pressure field V and pi in the reference configuration. So V and pi are simply pullbacks with respect to chi of U of our current configuration, velocity field and pressure. Okay, so now of course things get ugly because now I have to the goal is to rewrite my Stokes or even Navier-Stokes equations in the reference configuration. But of course, this composition here means that when I rewrite my equations, then I have to use the chain rule 1,000 times and I get a lot of nasty terms. So in order to be able to write these deformed equations in a somewhat compact manner, I introduced the notation you see here. So the cofactor matrix of the gradient of chi of u, I call A of u, the inverse of gradient of chi of u, f of u, the determinant of gradient chi u is j, and I use this, say, this is, well, we could call it the Cauchy, the fluid Cauchy stress in with respect to the reference configuration. So this is the fluid stress, Cauchy fluid stress tensor that you get when you pull it back from the current configuration to the reference configuration using chi of u. Okay, so last week I mentioned the Piola identity. Now the Piola identity is super important in this game here. We used it for the first time here to retain the divergence structure of our fluid equation in the current, once we rewrite them in the current configuration. So of course we in our current configuration fluid equations, we have the divergence of the fluid stress. And then we do the pullback, and due to the Piola identity, the pullback of this divergence again has divergence form. So this is not trivial. This is really thanks to the Piola identity. Okay, so that's actually one very nice feature, because this means that when we take our conservation of linear momentum, in the Navier-Stokes equations, which of course at the outset is written in the current configuration, we use the chi of u as a pullback to express the equations in the reference configuration. Well, we still have this divergence structure here, divergence of a of the tensor I call TUF. Okay, okay, the nonlinearity. B grad B, when we pull it back, we can write, or after pulling back, we get grad B AV. So now I use the notation. I don't use this V dot grad B notation anymore. Just use matrix multiplication, right? So the gradient of V as a matrix times the A of U as a matrix times the vector V. So quite a nice compact way of writing this stuff here. Okay, so mass conservation. Well, mass conservation is actually also where we really need the Piola identity. Now, in the first line here, you see the Piola identity. The Piola, well, no, the Piola identity in itself is just the statement that the divergence of cofactor matrix is equal to 0. And now the A matrix that pops up here everywhere, this is a cofactor matrix of gradient chi. So in this case, what I want to say is that when you take the divergence of this AU cofactor matrix times V, then well, then if you just without the Piola identity try to compute this, of course you will get many derivatives of your A matrix, right? But in fact, all of these terms disappear due to the Piola identity, and you end up with well, there's a nuisance factor here, determinant of gradient chi, and then the divergence of V. Okay, but the conservation of mass equation is divergence of V equal to 0, right? So the pullback to the reference configuration of this equation has the similar divergence structure. This is really thanks to the Piola identity. So yeah, our volume condition well, just change so the volume of the deformed, the volume of the deformed fluid domain, right, is integral over omega over the deformed chi u of the omega of 1 dx, right? But then you use the chi of x to rewrite this integral as an integral over over the omega, and then you get the Jacobian, the determinant of gradient chi of u, so my j here, in your integral. So that's how the volume condition, takes this form now. Okay, so where was I? Here. Okay, so here we have all the equations of motion written in the reference configuration in a thanks to the Payola identity in a fairly compact manner. Okay, and now after the pullback, of course, our fluid equations are now equations in V and pi with respect to or defined as functions on the reference configuration omega f. Okay, so now we can start to do mathematics because all the equations for the full system here is written with respect to a known and fixed reference configuration. So here's the main theorem of existence, which means that our coupled steady-state fluid structure system is well posed. We have to work in order to show this theorem, this is important, in LP framework of subler spaces with p larger than 3. In this case, we get for sufficiently small data, we get a solution uv pi to our equations of motion, of course, in written with respect to the reference configuration. Okay, so so this is the final theorem for the steady state. So this gives us existence of a steady state. So so how do we prove this? Well, I already said that I want to just use the good comprehensive linear theory, good comprehensive LP estimates for the linear operators to construct a fixed point argument. Now, in fact, I'm going to do it a little more elegantly. At least I think a little more elegantly. I'm not going to use a fixed point argument directly, but rather I will use the inverse function theorem. Of course, the inverse function theorem is just corollary, really, or the proof of the inverse function theorem relies on the Banach fixed point theorem. So it's the same thing at the end of the day. But when you show these things, I like to do it as elegantly as possible. And in this case, I think that whenever you can use inverse function theorem, you should really do it. Okay, so I need to introduce some spaces here. V2p gamma fs is the space of vector fields V2q defined in the fluid domain that have zero trace on the fluid structure boundary, and similar we define the next subler space V2p gamma s, and then we define a space V1p AVG average of g functions in V1p that have zero average over the fluid domain. Okay, so let's have a look why we need these operators. Well, so I need the spaces to define the operator that you see here. So this operator you see here is simply the operator, is simply the nonlinear problem, or nonlinear fluid structure problem put into operator form, or the left-hand side of our fluid structure problem expressed as an operator, right? So we have here our unknowns, which will be the arguments we put into the operator, and here we have the differential operator of our system. So we have first the elasticity system, divergence of our Piola-Kirchhoff stress tensor. Then we have the differential, the forces, the normal stress of the elastic on the fluid structure boundary of the normal stress from the elastic material and minus the normal stress from the fluid. This, of course, we want the solution to have zero balance of forces here. And we have the third component here. This is the so this is the left-hand side of our Navier-Stokes equations. The reference configuration here we have the divergence, left-hand side of our divergence equation, and finally here we have our the left-hand side of the volume condition, where okay, so now this operator here, it's well defined. It's not clear at the outset that it's well defined. You have to look a little bit. The orbital spaces here. One very important property of that we need in order to deduce that K is well defined is the algebraic property of B1p. And if for this we need the P larger than 3. So algebraic property in this case means that if you take two functions from this orbital space, multiply them with each other, you get you end up again in this space. So this is super important here because look at all the products of B1p functions that you see everywhere. So you have here, no? So if you take a W in V2p, right? So then the gradient is going to be in B1p, and the A of U, this is the cofactor matrix of gradient chi, but also the U is in V2p. This was here, right? So also all of the components in this cofactor matrix will be, well, remember how you compute a cofactor matrix? Well, you have to compute all the minors, and they are products of the components in gradient chi in this case. So we are multiplying a lot of V1p functions with each other, and we end up, we can do that and remain in the space V1p. So in order for such a nonlinear term like this to be well defined, we need the algebraic structure of B1p. This we only get, of course, if we choose the P exponent large enough, which means since we are working here in 3D domains, larger than 3. So this is one of the reasons why we need the LP theory to do this. We cannot rely on the 2P theory, at least not in a naive manner. So we turn to LP theory in order to be able to choose a large P. Okay, one more thing, and this is also really where the Piola identity plays a crucial role. If you look at our divergence equation here, well, if you don't use the Piola identity, just naively compute this divergence of AUB. Well, product rule, right? You get some derivatives of the A components times V plus A components times gradient of V. I wanted to say how this is not necessarily in V1p. Because yeah, of course not, because if you have derivatives of the components of the A matrix, so the A matrix, this is the cofactor of gradient chi. So chi is in V2p. So the U is in V2p, so the chi of U is also in V2p, and then the gradient will be components in V1p, right? And now you take a derivative of a function, so you end up in LP. So if you naively compute this divergence here, you get LP functions times V functions. It's not necessarily in V1p. Okay, but due to the Piola identity, the divergence all of these terms which appear naively, they in fact disappear. Due to the Payola identity, this divergence of a V can be written as the scalar product, is this colon here is a scale matrix scalar product between the A U cofactor matrix and the gradient of V. So we don't get these nasty derivative of A components due to the Payola identity. So it's a small thing, but it's really super important, because otherwise our nonlinear operator, once we refer everything to reference configuration coordinates, would not be well posed in the canonical setting here. But the Payola identity saves us, so that's important to note. Okay, so I can formulate the fully nonlinear problem that we are trying to solve as this one equation here. So my nonlinear operator K in U in P is equal to the prescribed forces. Well, we have, of course, the body force, the fluid equation, body force in the elasticity equation. Okay. So, well, observe that if we put in zeros in the K, we get zeros out. In fact, I can show existence of a solution for small data, Fe and Ff, if I can show that K is locally invertible around 0. But for this, I can use inverse function theorem. Now, in order to employ inverse function theorem, I need to verify that the Fourier derivative of my mapping K in 0 is an isomorphism. Then I get local invertibility, and then I get for small data F and E and FF a solution UVP. So everything reduces when you introduce this framework here to showing that the Fourier derivative in 0 of K is an isomorphism. Now, what is the Fourier derivative of K? Well, the Fourier derivative in 0 is nice, or is easy to compute, because this is exactly the linear operator you get when you just throw away all higher order terms, of course, with respect to your variables U, V, and P. So and let's do that in the different equations now. So for the Euler-Kirchhoff divergence of the Euler-Kirchhoff stress, we know that the linearizations of the linear terms in this expression, this is what constitutes our linear Lemmy operator, and the rest are higher order terms. Right. So the Fourier derivative of divergence sigma is our Lemmy operator here. The Fourier derivative in 0, that's important, right? Okay, our boundary condition, if we do the same thing, our boundary condition corresponding to the balance of forces condition, well, we can, when we linearize, again, we linearize the Euler-Kirchhoff stress tensor, we get the Lemmy tensor, and when we linearize our say deformed fluid stress, we go back to the classical Cauchy stress tensor for the fluid, and of course the rest are higher order terms. So just write every equation here. We have the Navier-Stokes equations we obtain by referring everything to reference configuration coordinates. We linearize everything. Well, then we have a Stokes operator plus higher order terms. And the same with the divergence equation. Finally, our volume condition, which okay, so the volume condition I will write as volume of deformed fluid domain minus volume of reference fluid domain equal to 0. That's the way I'm writing the volume condition, right? So if we linearize the left-hand side of this expression, then we obtain the integral over the fluid structure boundary of u dot n plus higher order terms. So why is this? Well, if you think about it, what is J of U? Here is J of U. This was the determinant of gradient chi U, and the gradient of chi. Well, the chi of U, this was the identity plus just the Sobolev extension of U. So the gradient of the identity function gives us the identity matrix, plus gradient of U. So I just write gradient of U instead of gradient of the extension of U. So if you compute this determinant, well, then you get, of course, a 1 just from the identity matrix sitting there, and then you get plus, and then you get well, due to the diagonal of the gradient of U, when you no, actually it's okay, I need a little bit of space, but so when you if you look at the diagonal of identity plus gradient of U, right, and you compute the diagonal product, well, you will find that you get d1 of U times 1 times 1 plus d2 of U times 1 times 1 plus d3 of U times 1 times 1, so you get the divergence of U, and the rest are just higher order terms. You compute this determinant. So writing J of U like this in this expression here, well, the integral over omega f of the 1 gives us the cancels out with the volume of omega f, and then the integral over divergence of U over omega f with the Gaussian theorem is exactly this term, and then the rest are just higher order terms. So this is the volume condition, or the linearization of the volume condition. Okay, so we conclude that the Fourier derivative of our nonlinear K operator is in 0. The operator which takes a U, V, and pi into Lemmy operator applied to U. On the boundary we have the Lemmy stress minus the Cauchy stress, and then we have the component of K corresponding to the Navier-Stokes equation. Well, the Fourier derivative, the corresponding component in the Fourier derivatives is the Stokes operator, and here the last the component in the Fourier derivative corresponding to the boundary, to the volume condition is the integral you see here. Okay. So basically, the Fourier derivative in 0. Yeah, this is of course an operator, right? So this is the linearization of your nonlinear system. So nothing more, nothing less. That's why we get the Lemmy operator, the Stokes operator, so forth. So yeah, okay. So that's the Fourier derivative. Now we have to show that the Fourier derivative is an isomorphism, and that's really just a fancy way of saying that our linear operator, our linearized problem, is an isomorphism in the setting of of LP Sobolev spaces. Okay, let's look at the kernel. So consider some element in the kernel of our operator. Well, we know from we already computed the kernel of the Stokes operator. And this is the so this is the kernel consists of all these constants here, constant vectors here. So we know that the pressure is so the V is 0 and the pressure pi must be a constant. Okay, so now we plug in this knowledge of V and pi into the linearized elasticity equation, so into let's say the equations corresponding to the equations of the two first components of our linear operator here. Here we have the two first components. Of course, we are looking at an element DUVP in the kernel. So we know that, well, all the components, when we apply our linear operator to UVP are 0, in particular the first two components. So this is this equation here. And now I have plugged in, of course, C for the pressure and 0 for the V. So I have this equation. So this is information on the U, and written in as a system of PDEs. You have the PDEs here. Okay, so this is what we know of the U. Now we just test with U. We multiply by U and integrate over omega E, and do integration by parts. Of course, this is a nice system to do integration of parts, right? Because I have here divergence of some tensor equals to 0 in omega E, and on the boundary I have the tensor itself again here equal to this constant vector here on the boundary. So doing integration by parts in this setting is an easy task, and you end up with well, of course you have 0, and then after integration of parts of the left hand side you have the integral that you see below. Okay, so so what do we know? Well, now, of course, this integral here, this is 0 because that's the expression for the linearization of the volume condition applied to U, right? So this is the last component here of our linear operator, dk, or Fourier derivative, right? But we are considering here U in the kernel, so the last component is 0. So this guy here is in fact equal to 0. Okay, so we have that the other integral is 0. But of course here this integrand here is positive, so we know that the divergence of U is 0, and the bold-face D of U, this is the symmetric part of the gradient of U, is also 0. So when the symmetric part of the gradient is 0, then the vector field is, I call it a rigid motion type vector field. It takes this form here. It is equal to A plus B vector product X for some vectors, constant vectors A and B. So but we have that our vector, our U is an element of a function space where U is equal to 0 on the outer boundary of our reference configuration. But and from this you can easily deduce that the two constants A and B have to be 0. So the U is 0, but when the U is 0, then from the previous equation we also get that the series 0. So everything is 0. Our kernel contains only the 0 elements. The kernel is trivial. We conclude that the Fourier derivative is injective. Now, to show that it's also surjective, it's onto, we consider, well, some element of what's it called in English? I forget. The right-hand side space here, right, of our linear operator. Consider any element, and now we look for UVP that maps into this element. Okay, but now we employ the homeomorphism properties of first the Stokes operator. Of course, since homeomorphism property is of course the one that I stated. Remember that in order for the Stokes operator to be homeomorphism, I had to factor out the kernel. So the homeomorphism property here gives us an element v pi, so that the Stokes operator applied to this element equals to our fixed right-hand side, but for all constant c, right? Okay. Now the Lemmy operator is a true homeomorphism. The kernel was trivial, so we easily find vector field u1 such that the Lemmy operator applied to u1 is equal to this fixed right-hand side. Now here to this right-hand side, I have added, you see TF, a normal stress from the VP element we fixed before. Okay, so I can also solve the Lemmy system uniquely with terms to right-hand side 0 n as well, 0 as the field equation, n as data in the boundary data, and now I need to deduce. Well, let me just say what I do here. I take my U2 vector field that I just found. Of course, the U2 solves the Lemmy equation with data 0 and n, right? Now I multiply my Lemmy system with U2 itself, so it's testing by U2, integrate over the domain, and we get the same kind of equation as before. So we get, yeah, so this expression. Now, if this boundary integral here is 0, well, then also the divergence and the symmetric part of gradient is 0. Well, in particular, the symmetric part of the gradient is 0, but this means that U2 is 0 by the same argument as I had on the previous slide. Okay, but this cannot be, because the U2 solves this boundary condition with non-homogeneous boundary values on my fluid structure boundary. So I conclude that this integral here cannot be 0. Okay, so I can use it as a scaling factor. Now I find some constant, so that well, this identity here is given. So gamma was the right-hand side, the data that we are checking that our Fourier derivative is onto, and so we fix some data in the data space. Gamma was part of the data. This was the data for the value. It's for the volume condition, linearized volume condition. Okay, so we can scale it like this. So why do we do this? Well, because once we do this, then we can add to the U1 this C0 U2 in order to get the gamma as the in the final equation, or in the final expression for the Fourier derivative of our K operator. Anyway, we show using well, not really more than so a little bit partial integration back and forth, that our Fourier derivative of K is surjective. So the most important things here is the two homeomorphism properties of the Stokes operator and the Lemmy operators. That's of course the main thing that goes into the proof here. Okay, so well, now we are done, because our Fourier derivative is an isomorphism. We can invert it. We can invert the K mapping. Therefore, locally around the zero by inverse function theorem and solve our problem for small data. This is all we wanted to do. So that's the main theorem for the steady state fluid structure problem. Now I have to say one thing, because I'm saying all the time Stokes operator for the AS operator. Do I have it somewhere? Okay, no, I don't have it. I've said it a million times. So here, for example, right, an AS operator. So this is, of course, the linearization of the steady state Navier-Stokes equation. Gives me the steady state Stokes equation. And when I put my Stokes equations into operator form, well, the operator I get, I call Stokes operator. This is a little bit dangerous because Stokes operator sometimes means something else. Often we have the Stokes operator in fluid dynamics to mean the Helmholtz the Helmholtz projection applied to the Laplacian. This will be our this is what is often referred to as the Stokes operator, which is clearly not what I have here. I have a different Stokes operator, so I apologize for if you are confused when I say Stokes operator. In lack of a better name, I've misused the term here somewhat. Okay, so that concludes the steady state part of the lecture. So really the takeaway from this part is that once we linearize our fluid equation and our elasticity equation, including the boundary condition, we obtain the coupling of two systems that are both elliptic in the sense of Ackermann, Douglas, Nirenberg. So we have comprehensive LP estimates for both of these systems. We have the Fredholm property of the corresponding operators, and so we have a setting where the coupling is even works with the inverse function theorem. I mean, when the coupling works with the inverse function theorem, you know, okay, everything has worked out beautifully. So in the steady state case, finding steady states seems, I will not say easy, but it seems that our equations of motion are certainly well posed when it comes to finding steady states. It works beautifully. So let's move on from the steady states to time-dependent fluid structure interaction. Now, time-dependent fluid structure interaction turns out to be a lot more complicated. Here we have the equations we derived last week. So this is the same equations of motions that I've been working with the whole time, but now in their original non-stationary form. I did not include here any initial values, by the way. This is just the non-stationary. Also, the volume condition I left out. Okay, so non-stationary fluid structure interaction. Here we have of course, we can consider this as an evolution equation of elastic material deforming in time, corresponding flow flowing in time. Now, of course, the data is prescribed body force in fluid and in the body, and the unknowns are still velocity, field pressure, and the displacement vector field. Let's linearize them because, well, if we let's think of trying to solve these equations using same kind of methods as in the steady state case, meaning we linearize, we establish LP estimates for the linearized equation, and then we use some iteration, fixed point iteration, a similar kind of argument to obtain solutions for the nonlinear case. Well, Here's the linearized equations of motion, and linearization makes sense. When you linearize, you basically go back to the reference configuration. So, but you can also think of writing everything in the reference configuration, then linearizing. Okay, then we have the linearized system, just as we did for the Stokes system. So, can we establish good the same kind of LP theory that we did for the steady state case? Well, actually not. In the steady state case, we had two elliptic systems. Now we have, well, a parabolic Stokes system, and boundary condition here belongs to the Stokes system, parabolic Stokes system, and we have a hyperbolic elasticity equations. Once the time, everything is time dependent, well, the time derivatives pop up everywhere, and we get a hyperbolic parabolic coupling. Now, first remark. Well, I claim, and I sketch also the proof, that the Stokes, what I call the Stokes operator, is elliptic in the sense of Akman-Douglas-Nierenberg. This is true, but when you go to the study of parabolic equations, of course you want to have the same kind of LP theory, but it turns out that when you go to the parabolic situations, the Stokes the Stokes resolvent operator that you need to analyze in this case does not satisfy the what is called Akman's ellipticity condition. So there's also a little bit of confusion. So the Stokes operator that I dealt with in the steady state case, this is in fact an operator that is elliptic in the sense of Akman-Douglas-Nierenberg. But if I go to the parabolic case and consider the resolvent type Stokes operator that you need to study in this case, then this does not satisfy what is known as the parameter ellipticity condition, or Akman's ellipticity condition. So in this setting, the Stokes operator doesn't even fall into what can be called or what is sometimes called parabolic parabolic in the sense of well, there are many senses, and there is the sense of Akman, there's the sense of Petrovsky, and now I'm going off on a tangent, so sorry about that. But I just want to mention that when we ask the question if this parameter ellipticity is satisfied for the Stokes corresponding Stokes operator, then this is not the case. But but this is not a big problem, because nowadays we have better methods. We know that we can establish a comprehensive LP theory for this Stokes problem. Here we can use of course, modern way would be to establish our boundedness of the resolvent Stokes family of resolvent Stokes operators. You can do that, and then you get a beautiful maximal regularity theory here for our Stokes problem. So we actually have nice LP theory, but we have to do it in a modern way. We cannot use this old Akman-Douglas-Nierenberg well, Akman-Douglas-Nierenberg studied elliptic problems, but then there were several who tried to extend their kind of their way of investigating elliptic problems to parabolic problems, and well, it's in the parabolic case it's more complicated. But anyway, nowadays we have the beautiful frameworks to show nice what we call maximal regularity for the Stokes problem. That's not a problem. But the second part here, hyperbolic Lemmy system. This is more complicated. Well, it's not complicated in itself. It's a hyperbolic problem. I do not have any damping terms here. So if I just, well, not any explicit damping terms. I'll come back to that in a moment, actually. So it's a hyperbolic system, so you have to live with hyperbolic regularity. And in fact, the fact that we have a coupling of a parabolic system and a hyperbolic system means that we have a mismatch of regularity. So let me just say it as as directly as that. Now, I tried just very roughly to sketch the problem, the regularity mismatch that we have here, because the thing is, if we look at the coupling, then we have, look at the coupling, we have the no-slip boundary condition, which is one coupling condition, and we have the balance of forces here, which is our second coupling condition. Now, the balance of forces condition, well, here you see first order derivatives of u equals, well, linear combination at least of first order derivatives of u equal first order derivatives of v, and zero order derivatives of p on the boundary. But so this means that v and u, at least with respect to this differentiation in space, have to have similar regularity, right? Because first order derivatives of v have to coincide with first order derivatives of u on the boundary. Okay. But then look at the second equation, the second coupling condition, our no-slip boundary condition. V equal to dt. Well, this of course means that v and dt of u have similar regularity, but and this is what I mean by mismatch, because I mean it's not out of, I mean, maybe you can find a functional framework where this kind of mismatch is not a problem, but you'll have to try hard, because if you try to do it naively, this is not an easy task. Now, I know, not because I did it personally, but because there are papers. There are some very long papers by Kutan and Scholar. They do this. I mean, we're talking about 100 pages long papers trying to establish the framework for functional function spaces, framework of function spaces, that sort of where you can where this kind of mismatch is admissible. It's not trivial. So there's not a natural way. That's my point really. In the steady state case, that was a very natural function space setting. Just B2P function spaces with corresponding trace spaces constituted a perfectly nice framework of function spaces where you could couple easily. Here, the situation is much more difficult. Of course, in the steady state case, you know, the dt of u is equal to 0 because, well, we're looking at steady states, right? So that helps you enormously. So this means basically that well, one coupling condition actually doesn't couple at all, because, well, the u part dt of u just vanishes. Okay, so that's one thing. Actually, now that I'm talking about this system, one thing I forgot to put in the slides. In fact, for the linearized system that we're looking at here, there's a very nice weak theory. Why is there a weak theory? Well, there's a weak theory because there's if you try to establish a weak formulation of this problem, so take a test function, let's take a test function phi and multiply it, just say take a 5 classical test function defined in the omega f domain phi, multiply it with the Stokes with this conservation of linear momentum Stokes equation here. Integrate by parts, as you do when you look for weak formulation. Well, when you integrate by parts, you will have a boundary integral, yeah. And in this boundary integral, you will have, of course, the Cauchy stress tensor that appears down here, integrated over the boundary. Yeah, okay, but this is equal to this Lemmy stress here, integrated over the boundary, times n, right? Lemmy stress times n. But then you can do Gaussian theorem or partial integration in the reverse, and go from this boundary integral to an integral over this guy. Well, not the full guy, no, over this guy or this divergence here, right? Okay, now you need also, of course, you need now that the test function, you need also test function defined on this space here, and the test function defined on the omega e space has to coincide with the test function with respect to the fluid domain on the interface. But you see, once you do this partial integration with respect to test functions, the boundary condition here actually disappears. So when you, after doing your partial integration, you will end up with a weak formulation where this boundary condition is not explicitly seen. It's hidden in the weak formulation, but this means also you don't have to deal again with two boundary conditions that are somehow not matching in regularity. In the weak formulation, this is hidden. So there was a paper by Gunzberger and who many years ago, 20 years ago now, with beautiful weak formulation of this linearized system, but you can't do much. This weak formulation, you can find weak solutions, but the moment you try to find to gain regularity, to obtain regularity, because this is just the linear problem, right? The ultimate goal obviously is the nonlinear problem. So you need to have some fixed point iteration going, and for this you need higher order regularity. This you don't get. So okay, summa summarum, there's a beautiful linear theory that's a beautiful weak formulation and corresponding existence theory for the linearized equations of motion here, but it doesn't seem to help you, or at least I don't know if maybe I think this could be a beautiful way if somebody could figure out a way to exploit the linear theory to solve a nonlinear problem. As far as I know, I think I put this down here. Okay, comprehensive LP theory is not available for the hyperbolic system. It's a hyperbolic system, so you got L2 estimates, but you don't get LP theory for hyperbolic systems. So as far as I know, the well-posedness of the fully nonlinear problem is still an open problem. This is hard to, this is a little bit delicate matter, because in fact, the papers of Kutan and Scholar, which are beautiful papers, very comprehensive, very long and very many ideas they use, but they never showed that there is an oversight in these papers, which has to do with this regularity stuff. And well, I don't know if this has been fixed, or if this still, as far as I know, it is still an open problem. So I'm not going to be able to give you any answers on how to solve the time-dependent 3D fluid structure interaction. Still, as far as I know, open problem. What I can do is I can try to couple 3D fluid equations with 2D elasticity. How does that work? Well, what do I mean by 2D elasticity? I mean thin elastic plates. What is a thin elastic plate? Well, a thin elastic plate is a three-dimensional structure whose length in one direction is significantly shorter than in the two other directions, right? So some plate omega, and then with a small height. So omega is two-dimensional. That's the point here. Okay, so in order well, of course, the idea of looking at thin plates is to ultimately use a 2D model to describe the motion of your structure. And by reducing everything in one dimension, you can hope to get maybe more equations that are easier to work with. So, and this obviously was the well, not obviously, but it was the goal of Kirchhoff and Love. more than 100 years ago. So in the 19th century, they worked on finding, both of them independently, by the way, on finding models for thin plates. I believe Love was the one who derived correctly a model, or what we nowadays would accept as somewhat correctly the derivation of the thin plate model. So he made two assumptions. Every straight line of the plate, which was originally perpendicular to the middle plane, remains straight after the deformation. Okay, and perpendicular to the surfaces which were originally parallel to the middle plane. So, okay, I don't want to dwell on this assumption. I just want to show it to you because it shows, well, they are not really assumptions that are, say, what we nowadays would accept as physics, I guess. I mean, why do you why does he make this assumption? Every straight line of the plate which was originally perpendicular to the middle plane remained straight after deformation. Well, okay, you can make the assumption, but it's not based on any fundamental physical principles. That's what I want to say. The thickness of the plate remains unchanged after deformation. Again, yeah, you can make the assumption, but why are you doing this? This is not physics in the way that Saint-Venant derived the 3D model. Okay, but anyway, Löw was able to use these assumptions and derive a model, which was, I guess, shown by Kirchhoff to be well posed. In fact, Kirchhoff used the model before Löw derived it, but he knew the model, I guess, but he did not justify it. Löw was the one justifying it, and anyhow. So, provided the height of the plate, which we call epsilon, is sufficiently small, a surface force acting on the plate can be formulated as, well, a function, well, approximately, of course, as a function just on the middle surface, which is our gamma. So, and the hope is now, of course, to reduce, and this was what Löw did, reduce the equations of motion just to equations stated over the gamma domain, our 2D domain. And Löw derived, based on his two assumptions, the model that you see down here. So there is some scaling going on, but essentially we have a dt of u3 plus bilaplasian of u3 is equal to the force g, or the third component of the force. Okay, so u again is the displacement of our plate, and we have here an equation for just the normal component of the displacement. So the nice thing about this model is it contains, or this first equation of the model contains only the displacement in normal direction. So this is called the two-dimensional flexural equation of a linearly elastic plate derived by Löw. There is, by the way, also equations for the other two components of the displacement, u1 and u2, and they satisfy, well, they are given by this expression here in terms of a zeta function, and the zeta function is a solution to a so-called two-dimensional membrane equation. But, and this is a remark here. Ah, no, not the remark yet. Okay, I'll make the remark in a bit. Okay, so the point is, in Löw's model, you also have, you essentially have two equations, one for the displacement in normal direction and one for the tangential directions. Okay. Here, my remark, as I said before, it's not 2D thin plate equation. It's not derived from principle of physics. But purely it is geometrical and mechanical assumptions that can certainly be questions. However, there are beautiful work of CLA and Dare, probably butchered that name, and Raoul in the 80s, who validated that if you start out with 3D elasticity model, linear elasticity, and let epsilon tend to 0, then in the limit, and of course you can ask what is the limit, and so there are many ways to compute such a limit, but they found a natural limit as epsilon tends to 0 of the 3D elasticity equation, and in this natural limit they retained the Löw-Kirchhoff model. So that certainly justifies to a certain extent the Kirchhoff-Löw model. So it's not completely non-physical. And in fact, the model has been used for many years, still is today in engineering, to compute deformation of thin plates. So it can't be that far away from real physics. And the result of CLA also indicates this as well. One note on this result here: in order to compute this limit, they have to make some, again, non-physical assumptions and technical assumptions on how forces scale when you go to the limit, and so it can also be questioned. But it's a good, very nice result that gives, to some extent, a validation of our 2D model. Okay. Furthermore, the second equation, that was the so-called membrane equations. Well, there are epsilons everywhere, both in the flexural equation and in the membrane equations. And if you look at the epsilons, well, the membrane equations have the order of the epsilon is lower. This means that the solution to the membrane equations is of a higher order compared to the solution to the flexural equations. So if we disregard the membrane equation as higher order terms in this model, you end up with just the Kirchhoff-Löw flexural equations as a model that you see here. So the only unknown in this case is the displacement U3, so displacement in normal direction of the plate. Okay. dTu, constant times dTu plus a constant times Laplacian u equals to some force G3. The corresponding solution U, or U3, is the displacement in normal direction in this case. So that's our thin plate. So now I'd like to talk about thin plates. Now, and I like to talk about the coupling of thin plates with a viscous fluid. First of all, it's interesting that it works. Well, not so interesting. Well, you have better chances because you have here bilaplacian. So this bilaplacian regularizes quite a lot in the coupling. I'll get back to that. That's not clear at the moment exactly why. So it's interesting that we can couple plate equations with viscous fluid, at least if we introduce damping terms. I'll come to that in a bit, but they couple. It's easier to couple them from a regularity standpoint than the 3D coupling. Okay, so but I like these thin plates. And in fact, this also has connections with the regularity issue. But I like the thin plate because there's an interesting problem of resonance, or at least when you couple the plate, then you have an interesting problem of concerning resonance. But let me start by talking about resonance in an elastic plate. So if here you see a flat plate, so a plate in a stress-free configuration. Now I'm going to apply a periodic forcing to this plate, right? So a periodic forcing, well, I take the whole of the real axis as a time interval because, well, when I have periodic forcing, I don't really have any time zero. So for technical reasons, when I do periodic forcing, I can just assume that I have such a forcing on the whole of I can have my time axis is the whole of the axis. That's just a technical thing. That's absolutely no influence on what I'm about to say now. When you have a periodic forcing, well, of course, whenever you are forcing on the plate will deform, and you have a corresponding displacement u in normal direction. So from now on, I don't write u3, I just write u. So my u is displacement only in normal direction. I work with elastic plates from now on. Okay, so now here we have the equations of motion. So for simplicity, I put all the constants equal to 1. We are mathematicians, so we're allowed to do stuff like that, I guess. Now I want to just have a look at resonance. So I do the simplest thing I know how to do, namely periodic boundary conditions on my plate. So I take a square interval 0, 1 times 0 interval 0, 1, right? Put periodic boundary conditions. Okay, when I have periodic boundary conditions, I also need to introduce a vanishing average. So that's my boundary condition essentially. Okay, so why do I want periodic boundary conditions? Well, periodic boundary conditions are nice because then essentially I can reduce my spatial domain to a torus. Okay, then I don't have a boundary. That's the point. So I don't have to fight boundary values. Just to understand the resonance, we do. It's a simplification, of course. It's quite well. Yeah, I think it's well, maybe you could justify in this case periodic boundary conditions. But anyhow, so just to mathematically understand resonance, let's look at the simplest case. Okay, now what is a differential equation formulated on a group? Because the torus here, I say torus, but I mean this group are factor group respect to C, right? So just to be clear, whenever I work in this group setting here, I say that a U in this group setting is a solution if the pullback to the Euclidean case here is a solution to the classical boundary to the classical equations. So okay, so much for the formulation on the torus. Now, solution to this linear problem is either growing in time, which I will call a resonant solution, or is periodic. Now, what's it? T-time periodic. This T here, I forgot to mention, this is the periodicity of my forcing term. Okay, so apply a periodic forcing term with period capital T. Then the corresponding solution to this linear equation is either, again, T-time periodic, which would I call non-resonant, or it's growing in time. So I mean, this is just, you can reduce to ordinary differential equations in the different variables and check that this will be the case. So the question is, well, no, not the question. This case, well, the question is, when do we have resonance and when do we avoid resonance? Well, in this linear case, it's quite easy to identify when we have resonance. Because I can characterize when I have a T-time periodic solution. What I do now is I replace the time axis with, again, this torus and obtain a very nice setting where everything is T-time periodic. And I look at my equation in this setting here. So, and the nice thing is, here on these groups, I can apply Fourier transform. I come from my background is so many years ago, studied a lot of abstract harmonic analysis, and when you study abstract harmonic analysis, you learn that the Fourier transform is a Fourier transform with respect to a group. So hence my notation down here. This is the Fourier transform with respect to the product of these torus groups that you see here. Now, we don't need abstract harmonic analysis today, because the Fourier transform of a torus group is nothing but expansion into a Fourier series. So what I'm essentially doing down here is I'm expanding my functions into Fourier series with respect to time and the two spatial variables, right? So everything is periodic. Both my functions are periodic in time, and they are also periodic with respect to the two spatial variables. So I can just expand everything into Fourier, or I can expand into a Fourier series with respect to all the variables. Okay, I do that here. Of course, the dt square. After I Fourier transform, I get this symbol here. By Laplacian, I get this symbol here. I have the 2 pi over t nuisance factor, and more importantly, I have k squared and h comma j to the power 4th, corresponding to my hyperbolic my operators in my hyperbolic symbol in my hyperbolic equation here. Okay. So the Fourier transform, I mean, whenever you can Fourier transform directly, you can easily, at least formally, obtain a formula for your solution, because you can just so applying the Fourier transform, you get this equation here, right, for the Fourier transform of u, and now we can just at least formally divide by the symbol and use the inverse Fourier transform, and then we have a nice formal representation of our solution. Now, and I can tell you exactly when this U solution you see here is not only a formal solution, but a real solution, in fact, a real T time periodic solution. And this is the case when the denominator here on the right-hand side doesn't vanish. Because then, of course, the expression is well defined. So if I don't have any zeros in the denominator, then then the expression for u is well defined, and we obtain obviously a solution. So, well, actually, if I can have singularities here in the symbol. I can have singularities in the symbol, but only when the other guy, namely the Fourier transform of my data, is 0. Well, at those points where my Fourier transform of my data disappears, there I can have singularities. So if this is the case, and this is the condition I write here, this is the case, then there's formula you see up there is also rigorously correct and gives you a T-time periodic solutions. Okay, what you can also show is that when you have a singularity, that's a bad singularity. So if you have a singularity in your symbol here, at a point where your data of Fourier transform of data doesn't disappear, well, then what you are inverse Fourier transforming is not well defined, and so actually this formula, the formal representation up there is not correct, and that's the case when you don't have a time periodic solution, and this is the case where you have resonance, the time periodic solutions. Okay, so just to compute, I just wanted to compute at some point just one resonance solution, and this I did. So if you take the resonance, obviously this condition here means that your hyperbolic operator, the zeros of the corresponding symbol have to coincide with the zeros of the data. So this means that your data has to excite, or has to excite certain frequencies. in order for this condition to be met. And these are the resonancy frequencies. And in my case, where I have normalized my constant, my resonant frequency is 2 pi. So if I choose a period 1 over 2 pi for my data, I get resonance. Okay, so here I computed. I don't even know anymore why I came to exactly to this data, but anyhow, there was an idea behind it. The point is, I can give you here nice periodic data, which gives you time periodic data, which gives you a growing solution because there's a t factor here. So you can prescribe time periodic data, and the corresponding solution is growing in time. It's not time periodic. So this is the case of resonance, right? And this is also physically clear what's happening here. So you have a force that excites your structure, and well, pumps energy. So you have a force that you're applying to your structure, and this force over every period may pump energy into your system. I mean, that would be the expected outcome, right? That you have over every period a force that pumps energy into your system. So your system, your system, well, it's a hyperbolic system. There's no damping. So the energy just stays in the system. So your displacement just gets wilder and wilder. That's the resonance. So yeah, you're pumping energy into a system that doesn't have dissipation. So what do you expect? Of course, the resulting solution will be something that explodes in time. So it goes to infinity here in this case, right? Okay, so but what if we dampen the system? So here I dampened my plate equation with, you see here in red, dTu. This is a classical damping term. You can even physically, I guess, argue that this is a correct type of damping. So this is a damped elastic plate. Now, when you do the same exercise as before, you Fourier transform, well, due to our red term here, we get a damping in the symbol. Now, you see that dTu produces in the symbol here an imaginary part, right? But the other part of the symbol, there is a real number. So clearly, the damping, due to this imaginary nature of the symbol, or the part of the symbol corresponding to the damping, well, the symbol doesn't have any zeros. So in your representation formula, your multiplier expression here doesn't have any singularities. So you have, for any data, f doesn't matter. I mean, sufficiently regular, of course, with vanishing average. You have a t-time periodic solution. Okay, so you see immediately why a damping term gives you here a non-resonant solution. Simply just make sure the damping term, make sure after the Fourier transform that your multiplier doesn't have any singularities. You could do this with any pseudo differential operator whose Fourier transform lies on the imaginary axis. With the same argument, you get damping. Okay, and if you have worked with Fourier multipliers, you know that the decay of your symbol determines regularity of your solution. So this is also important, because if you have damping, the higher order damping you have, well, the faster your multiplier will decay. So the better regularity your solution will have. The higher order damping term, the better the regularity of your solution. That's the second takeaway from this easy exercise here. Okay, so I claim, make the proposition. So this is not a mathematical proposition. This is just my claim, is that the growth of the symbol of a damping term quantifies the damping effect. Yeah, So whenever you have a damping term, if you want to quantify how much does it dampen, just look at the symbol. Yeah, the growth of the symbol is in itself a quantification of the damping effect. Okay, let's come to the fluid structure interaction. Now we take our plate and we put it on we clamp it onto a container of water or any viscous fluid. Yeah, and then we apply periodic forcing. So now we have now we have a plate interacting with a fluid in a container, right? So well, it's a free boundary problem. We have a hyperbolic parabolic coupling, but very importantly, now, of course, due to the coupling, energy, the kinetic energy from the plate will turn into, well, kinetic energy in the fluid, of course, but moreover, in the fluid we have friction, we have a viscous fluid, so kinetic energy will also dissipate into well, we do in our fluid. We have a dissipation, energy dissipation in our parabolic fluid part. So, although we do not introduce directly a damping term in our plate equation, due to the coupling, at least from a physical point of view, surely the fully coupled system has a damping effect. So now the big question is, can we quantify this damping? Because it's not the damping effect. It's not a damping term like you usually have. Damping comes via the coupling with the fluid. Can we quantify it? And is it enough to ensure that resonance does not occur? This is a super interesting question, I think. And so I worked and tried to solve this question. Here again, can we quantify the damping effect of the viscous fluid in the coupling? That's what I want to answer here in the final part of my talk. So let's look at some mathematics. Well, we have an elastic plate. Again, I take just a square plate. Then I have a container with fluids, and of course, U is the displacement in the normal direction. So my 3D container, the lid of the container, or the plate, the upper plate of the container, obviously it deforms. So my container, the geometry depends on time. Okay, so here we have the equations of motion. Then we've seen them many times, just the Navier-Stokes equations in our unknown or our moving domain. It's also unknown and moving. So here the equation of motion for the elastic plate. Now we have our force that is exciting the plate, so it's a periodic force, and we have, of course, due to the coupling with the fluid, the stress coming from the fluid. So we have what you see here. You see the fluid Cauchy, so the Cauchy stress tensor of our fluid TF, right? Times capital N. Capital N is the normal vector on the deformed plate. So this is the normal. This is the classical normal stress that with which the fluid acts on the plate. But in our model, we consider only forces in normal direction. So there's a projection here until in the normal direction, and this normal is the normal of the flat plate of the current configuration. So it looks a little bit strange, but this is in fact due to the model that we're looking at. We have here two normal vectors: current configuration normal capital N and reference configuration normal small n. Okay, so here in red, this is the force coming from the fluid. So if the fluid is so via this force, of course, energy can be transported into the fluid, and in the fluid, the energy may dissipate, and so I claim, and I will back up this claim in a moment, that this red term here, the coupling condition with the fluid, acts in fact as a damping term. It dampens the plate motion. Okay, so we have a further coupling condition. We, of course, we have the force, balance of forces, as we called it in the 3D case, and we have also no-slip boundary condition. So the classical no-slip, we saw it several times. Unfortunately, I have to work with periodic boundary conditions. Unphysical, I don't like it, but it makes the mathematics so much more, so much easier. In fact, I don't have any, I don't know yet how to get rid of these periodic boundary conditions. No-slip boundary conditions, okay, I just mentioned those. Okay, I go into this turbo setting. I always mentioned this. So instead of the time axis, I choose this torus here, and in space instead of the plate as a subdomain R2, I use the torus, because then the periodicity becomes intrinsic into my built into my function spaces. So that's just a very convenient way of working with periodicity in time and in space. Okay, so here again, the container with fluid, we saw that already. And here again, the equations of motion. So we have the Navier-Stokes equations. We have the, well, we have everything we saw on the previous slide, just put into one system of equation. I don't think I added anything new here. Of course, we have that the fluid adheres to the boundary on the bottom, yeah. So we have a lid on top of the container, and the bottom of container is just part of the container where we have no slip, and then in the x and or what I call x1 and x2 direction, we have periodicity. Okay, so in fact, it's not a it's a cell. I should call it it's a cell in a periodic structure. That's what it is. Not really physically correct to have such. Okay. Anyway, so we just want to learn about this effects, and so we stick to the slightly unphysical but mathematically more convenient setting. Question again. The question is I posted several times: is the damping coming from the fluid enough to ensure that that we have a non-resonant solution that is a time periodic solution, and can we somehow quantify the damping? Okay, so now I'm going to do what I did several times last week and this week. We have to go from the current configuration into a reference configuration. Okay, link at the left you see on the top of the screen left, you see the reference configuration, and on the right, you see the current configuration. And we need a mapping that takes the reference configuration to the current configuration, right? So this was the mapping that I've used the extension operator in the 3D case. Extension Sobolev space extension operator to construct. And if you look, there are papers on these kind of things. In fact, there are papers in fact, Professor Shibata wrote some papers on similar models here, and there are others as well. Mathieu Hilliard in Paris written a number of papers also, and Céline Gramont on this kind of fluid structure or fluid plate interaction. And in many of these papers, and they use I call it bad choice. That's a little bit offensive, but the extension operator you see down here, it's a natural way of constructing the extension operator. So you take the displacement u, which of course is a function defined only on the flat plate, and then you multiply it with some say color function, yeah, some chi function, which is equal to 1 when the y is 1, and then goes to 0. So then you sort of in a very naive way just extend the u function to be a function in the whole of the domain, and well, using this this extended displacement vector field as a displacement, you construct a deformation. So I say that this is a bad choice. It's not necessarily in all cases a bad choice. If you have damping in your system, as many people do, because damping means you have better regularity of your solution. Well, if your damping ensures that your solution has good regularity, this is not a bad choice. But if you are fighting on the cusp of regularity, then this choice actually is a bad choice, because you lose regularity when you use this phi to reformulate your equations of motion from the current configuration into the reference configuration. Why? Well, here I use just the extension operator that we also used in the 3D case, by the way. Why am I extending the U? I also use the cutoff, by the way. Yeah, okay, so yeah, because yeah, okay, I still use the cutoff, but the point is, instead of I should not put so many yellow rings here. So I use here the extension of U, and by extension of U, I mean I employ the extension operator that we have available when we work in Banach spaces. I haven't specified the Banach spaces, but that's the extension operator I'm using here. So why is this extension important? Why does it give you a better choice? Well, because extension operator is the right inverse of a trace operator, right? Now, if you think of a trace operator in a Sopland space, well, when you take the trace of a function, you lose regularity, right? So if you take the trace of a function in V2p, the function is the trace is a function in V2 minus 1 over p. Okay, so you go to the trace, you lose regularity. Interestingly, you lose regularity when you have a time-dependent function. You also lose regularity in time. Or if you have a flat surface, you also lose regularity in the tangential directions, which you at the outset, when you think about it, it's strange, but that's how these extension operators work. So in fact, when you imply a trace operator, you lose regularity in time and in space. But this means that when you employ the extension operator, you gain also regularity in space. So the difference between my U and my extension of U is that I have the extended U, in fact, has better regularity in space. So I'm gaining regularity with the extension operator. There's a subtle, but and you're on the cusp of regularity. This is an issue. Okay, so the rest is now we do similar stuff as we've been doing all day, right? We take our deformation or our mapping, that's capital phi, which maps the current configuration, the reference configuration to the current configuration. We use it as a pullback. And use it to rewrite our equations of motion. Of course, for the fluid, this is those were the ones who were written in the current configuration. Now we rewrite them in the reference configuration. Okay, and we see the cofactor matrix that I called A before, and the gradient of the chi inverse, which you can also express in terms of the cofactor matrix appearing everywhere. It gets messy, of course, sure it does. But we now have equations of motion written in the current configuration. Okay, so yeah, it gets messy, but now we linearize, and then we try to find a good setting of function spaces, but this linearized or the corresponding linear operator has nice mapping properties, and then we hope with a fixed point argument or similar stuff to be able to establish the existence of for the nonlinear system. So here we have the linearized equations of motion. Okay, or at least I put all the nonlinear terms on the right-hand side. F1, F2, F3 are the nonlinear terms in my system. Okay, so actually the linearization is a little bit I should, well, interestingly, and this is the computation, the only term that is linear in the in the fluid part. Let's go back to the nonlinear stuff here. Here we have the stress coming from the fluid acting on the plate. Now, when we linearize this this expression here, the only linear term is the pressure P. Okay, it's a computation. So anyhow, so now of course you can think about the pressure P as a function of U, right? Because for any U, you have a Stokes problem here for your V, and in particular your P, which you can solve. So so you can construct a mapping that takes a U into a P, right? And so this is what I mean here by P of U. So now, why do I want to write this P as P of U? Because then we can think of it as some damping term. You remember I said you can put any pseudo differential operator in U here, and then you can think of it as damping. And this pressure, I can in fact, and this is the nice part, I can express it in terms of a pseudo differential operator in U, and do just that. Investigate it as a damping term. So, so my elasticity equation obtains a damping from the fluid. So we see this here in the linearization. So the damping is not higher order. So the damping here is a linear term in the fluid structure system here. Okay, so so the goal, of course, now maybe this damping effect means that we can find good function spaces such that the linear corresponding linear operator is a homeomorphism, and then we can do the fixed point stuff. So let's look at the linear problem. Okay, now I do some technical stuff. I introduce a time averaging operator, capital P, which just integrates function over the time. So the P of U is time independent. Then I introduce a Fourier transform. Okay, on the tools times Rn. So this Fourier transform on my group here corresponds just to a Fourier series expansion with respect to the time variable, and a classical Fourier transform with respect to the spatial variable in Rn. Then I need some spaces. Now I don't want to go too much into the spaces, but so I need to work in anisotropic Sobolev spaces. And I define them as, in terms of my Fourier transform in this setting here, as anisotropic Bessel potential spaces in this way here, right? So I just HRS are the functions U in L2 with respect to time and space, such that the Fourier transform of U times k to the power r. So k is the symbol corresponding to Fourier transform in time, and psi is the symbol or variable corresponding to the Fourier transform in space. And so we can define Bessel potential or anisotropic Bessel potential space in this way. This is not, I mean, it's not in textbooks, but you find it in papers. So when you need it, this kind of spaces, you can define it. Okay, I need to work in these spaces, so I need embedding properties, and you can show this. And I need the trace theorem. So I need to take the trace of functions in such Sobolev spaces, in Bessel potential spaces of this type, in half spaces. Of course, I can take the trace, which is then a function on the plane. of the Haas space. Okay, and you see when I take the trace, of course, I go from R regularity in time to R minus R over 2S and S minus 1/2. So I lose regularity in both in all variables, both in time and space, when I take the trace of a function, and when I then do the extension, well, then I gain from A to A and B to B plus 1/2. So okay, this now gets a little bit messy. So you see, I gain regularity from the extension operator. So okay, so again, when I differentiate with respect to time, I actually also lose regularity. And so this is just my Bessel potential spaces that I need for this particular application here. Unfortunately, they are not part of standard literature, so I have to define them myself and prove the space theory, trace theorem, and Sobolev embedding and stuff like that. But okay, can be done. Okay, so now I decompose my system into a Stokes system and a fluid structure system. So this is interesting. So what I do here, I take, so I have, if I just go back, sorry, here to my linearized equations of motion, right? So I have an F1, F2 right-hand side in my Stokes equation, and an F3 right-hand side in my plate equation. So now I do a decomposition where I consider one Stokes system with respect to F1 and F2, and then one fluid structure system with a fluid part, a Stokes part with homogeneous right-hand side, and then the only inhomogeneity is in the structure part. Okay, so this decomposition is actually quite useful. Why? You'll see in a moment. So here is the damping effect of my here's the damping effect of my fluid stress quantified in terms of regularity parameters. So if I start out with some H, so H, by the way, this is the right-hand side, the forcing term on my plate equation. See down here. Start out with some H, which needs some regularity. By the way, the complement here means that there's a function space of functions that had zero time average. Forget about that for the moment. I want to explain this. The important thing here is this space here. Okay, so I start out with some H forcing term, and then I claim that there's a unique solution to, and this is just the second part of my decomposed problem. So with the homogeneous data in the fluid part here. Okay, so I claim there's a unique solution, V, pi, and U, and the U lies in the space H2 with exponent 3/2 describing the time regularity and exponent 7/2 describing the spatial regularity. So when I take a H in this space here, I get a solution U to my plate equation, which has, well, we are going from 0 regularity in space to 3/2 in space, and 1/2, sorry, in time, and 1/2 in space to 7/2 in space. So I gain 3/2 irregularity in time, and I get well, I started with 1/2 and I go up to 7/2, so I get 6. No, 4. No, I get 3. Sorry, 3 plus 1/2 is 7/2, so I get 3. At this additional orders of regularity with respect to differentiation in space. So this is the regularity of this problem here. Okay, it's a hyperbolic. So it's a hyperbolic parabolic coupled problem, and it's the crucial part of our fluid plate problem. Here in this lemma, I see exactly how good the fluid dampens the plate, and it's expressed, quantified in terms of these irregularity parameters here. Okay, so let's have a look at the proof. So this is quite standard actually, and because I have the homogeneous right-hand side here, I can I can first apply the divergence to the fluid equation to get rid of because the divergence of V is 0, right? So if I apply divergence to the fluid, the first equation in the fluid system here, I get just the Laplacian of P equal to 0. So then I apply the Fourier transform. Now, this is a half-space problem, by the way. Oh, I didn't emphasize this. This is a half-space problem. So my fluid equation is in the half-space. But I can still Fourier transform with respect to time and with respect to tangential directions. I do this now. Of course, the normal direction in my half-space remains as a derivative. So I get an ODE, but I can solve the ODE. Okay, classical solution to my ODE. It's an ODE in X3, right? So my Xi and my K, my Fourier variables are constant. So I get this solution here. Okay, so now I apply the Fourier transform to the original equation. I plug in what I know about the pressure here, and I get ODEs, and I can solve the ODEs again. Okay, I'm not doing the details. I'm just sketching the proof here. So Fourier transform again, but now the original fluid equations. Before we transform, of course, only in tangential direction, meaning implying that one order of differentiation remains. So we get an ODE for the Fourier transformed quantities. These ODEs we can solve. And well, at the end of the day, utilizing the divergence of the V0, I actually get an expression from I get by setting x3 here equal to 0, x3 equal to 0, and exploiting divergence V of 0 in these equations up here, actually get an expression for the Q. Okay, so and the Q, this is the Q naught. This was in fact, we can identify it with the other way around. The Q was was part of the solution to the ODE, in which we found the pressure pi, and in fact, when the pressure pi or the Fourier transform hereof at 0, this is the same as the Q. So at the end of the day, we find the Q, and it's equal to this. Yeah. Of course, the U dependency enters into the game here, which is of course due to the no-slip boundary condition, right? So the U enters into the fluid equation. We have a coupling, and via computations here, I get my pressure beautifully expressed, at least the Fourier transform of my pressure beautifully expressed in terms of the U displacement field. So now I have my my pressure as a function of U, right? And you see here, in fact, it's a pseudo differential operator in U, right? That's the symbol here. So I have my pressure expressed in terms of a pseudo differential operator applied to U. So now I plug in the corresponding symbol of my pseudo differential operator, and I get the damping term coming from the U. So I know I can now look at the damping that the fluid is exerting on my plate. I can look at it directly, which is beautiful. And the damping term here, well, what is the problem in this symbol here? This is a hyperbolic symbol, so I have this hyperbolic part. Okay, the hyperbolic part means that in my symbol I have a singularity, namely when the psi to the power fourth is equal to k to the power 2. But since I now have a damping term, which is imaginary, right? That's the important point. Well, when the psi to when the psi to the power fourth is equal to k to the power 2, then the damping term steps in and delivers me something which is to the order k 3/2, which is why I gain 3/2 derivatives in time. But similarly, I can also express this damping term and speak, or at least look at the order of the damping term, and it has the same order as psi to the power 3. So it tells me I get 3 extra derivatives. This is a regularity that I gain due to the damping term in my hyperbolic equation. Now here I compare to some classical damping terms that are used in the plate equations. Of course, classical damping terms have nicer symbols, but well, they're damping terms. The beauty of my damping is that it comes from the fluid, so it's a physical damping that I can now quantify. Okay, so I'm almost finished. Let me wrap everything up here. Now I can quantify the damping. So here you see a lemma which states that I can solve my my inhomogeneous Stokes problem in my setting of my function spaces. This is just classical Stokes theory for the Stokes problem. I'm not going to go into that. No, here's my final theorem. When I prescribe a periodic forcing on my plate, I can find a unique solution with a displacement vector field which has gained 3/2 derivatives in time and 3 derivatives in space with respect to the forcing term expressed in my anisotropic Bessel potential spaces here. And this is enough. This is enough regularity to start a fixed point procedure. We are on the cusp of regularity. It's not much. So I need also this good extension rather than the bad extension, but it suffices. So due to this damping coming from the fluid, my hyperbolic solution to the hyperbolic problem has enough regularity that enables me to carry out a fixed point procedure. So here, this is basically just stating, the proof states just that, right? So I start out with some B tilde P tilde U tilde, plug these quantities into my nonlinear terms, verify that in my setting of function spaces, and here in particularly, I mentioned the function space here dictated by the regularity that I gain for the hyperbolic solution due to the fluid damping. I can plug in such a B tilde P tilde U tilde into the nonlinearity, end up, I have to check of course, but I check that I end up in the right function spaces, right meaning that my nonlinear terms can be when I put them on the right hand side and solve using my lemmas, I get solutions here first to the Stokes system and then to my fluid structure system. I get a solution which is again in the right space. So I have an iteration procedure, and I have also the estimates, and which enables me to obtain a fixed point with Banach fixed point theorem. So the estimate is with the regularity gain, the quantification of the damping from the fluid, that helps me. Okay, so my last slide. So this what I showed you here is a problem I've been studying for some years now. In the periodic setting, I can solve it as I showed you, and that's nice because it shows you that, well, as I said many times now, the fluid actually dampens the plate, the hyperbolic plate, sufficiently to that we can find a periodic solution, and therefore we can answer the question if the damping from the fluid is sufficient to avoid resonance. Yes, in this setting where everything is periodic. Well, certainly where the spatial geometry was this cell, my periodic boundary conditions, they are not physically reasonable. So what I really want to do, of course, is to extend to some physical geometry where I have not periodic boundary conditions, but no slip boundary conditions on the lateral part of my container. And this I don't know how to do because there's technical stuff with the coupling, and that is something that is really annoying, because I believe that the heart of the matter lies in this quantification of the damping that I can do already. Okay, so that's work to be done in the future. If you're interested, you're more than welcome to join me on these problems. I think there are many interesting open problems in this fluid structure interaction. I described two today. Here's one, and also with the 3D cobbling of 3D elasticity coupled with 3D fluid flow. Also super interesting, and many open questions. Okay, so I've reached the end of my time. So I want to thank you very much for your attention, and thank you for giving me the opportunity here to lecture at Waseda. Thank you so much.
Thank you very much, Matt. It's a quite nice lectures for me. And also thank you very much. Your time, you use a lot of time to make preparations. It's a very great job. Right? Thank you. I'm very impressed very much. Do you have any questions? I ask you, the audience. Do you have questions? Yeah, actually, it's a very difficult subject, I think, especially. But by the way, the very technical questions, may I? What to say? Oh, pure identity you used, right? Pure identity. But this is hold for JU equal one case, or for any JU? Do you hear pure identity? So you use it in the stationary problem. I think maybe.
So I use
divergence V is equal to after the change of variables. Divergence V is equal to divergence AU W, I guess.
Yeah. So I had the pure identity. Yeah. Was it here? So this is this is the pure identity. So the divergence.
Okay. So that divergence coefficients. Okay, I see. But then maybe a variant version of this. The you use the div B. Div B is equal to div AU W. Well, I don't know. But anyway, this is very useful for your argument, I guess.
The yeah. So of course, when you do divergence of, actually, like this, divergence. Oh, sorry.
Yeah.
Just a second.
No, it's okay. Yes. Okay, so maybe I will check the proof. It's very geometrical proof, I guess.
So divergence of the cofactor matrix of gradient phi times a vector. So this I had in the proof. And of course,
because of the coefficient,
use this one to to compute that this is the cofactor matrix of gradient phi.
I see.
And then the scalar product with the gradient of V. So this was very important for, for regularity, because you see, I don't actually differentiate any components. So on the right hand side here, there are no derivatives of appearing of entries in the cofactor matrix.
I see. I see. Yeah.
Although one should expect that when you have here the divergence of this matrix times V, but surely when you employ the chain rule, you expect components of the matrix to be differentiated and to appear in this expression, but in fact they don't.
Yeah.
Which is quite extraordinary, and this is super important, because otherwise the regularity would not work.
Okay. Yes. You lose the regularity. Yeah, sure. Okay. Thank you. And also, maybe I almost your formulation of the time-dependent case. Actually, you said that you have some derivative rules for the equation. Yeah. Hyperbolic part.
Yeah.
Yeah.
So here's the
I
time.
understood this. Yeah, but yeah, more than 30 years ago, I worked on some hyperbolic problem with derivative loss. Then I have some of the some kind of trick. If you differentiate.
I studied your papers, by the way. You used this very nice trick, if I remember correctly. Sorry to interrupt, but you transformed the Navier-Stokes into Lagrangian coordinates. Is this the trick?
No, I talk about the hyperbolic part. If
Okay.
you have any derivative rules of the hyperbolic equations. For example, more than 30 years ago, I solved a fully nonlinear program for the hyperbolic equations without okay. But then that case is I differentiate hyperbolic equation once in time. And then you put dt u equal to v or w, so w, right?
Yeah.
And then I feel that you get regulators.
Okay. Actually, I want to one day work with you on this problem, because I wrote you have a lot of nice papers on this also, where you treat, as I said, where you transform your Navier-Stokes, go to Lagrangian formulation of Navier-Stokes.
Yeah.
Because then you have that's also an idea to get into a setting where the regularity fits, because then you have a Lagrangian formulation, which may actually be useful. So I know that you have a lot of knowledge that I want to someday.
Okay. Yeah. Okay.
what you can do with this problem, because it's yeah. I believe it's still open. It's a little bit delicate, because there was already papers by Coulthard and Scholar, but there were mistakes or oversights in these papers. So
okay. Yeah.
So I think it's still open.
I see. Yeah. Okay. So because I just give you think about some of the very rough idea to how to recover the derivative both for the hyperbolic part U.
Yes. So one other trick. You can do the same trick in the parabolic part. Also differentiate with T. Well, you can't, because then you differentiate the pressure with T, and you don't have any information on the pressure. But if you could do that in a differentiate with respect to D and get some regularity for dt squared of V.
No, it is not good, because the parabolic part is time differentiation is corresponding to the second derivatives, two derivatives in space.
So you get too many. So you get like a half a derivative, something like that.
But the hyperbolic part, one derivative is corresponding to one space derivatives, right?
Yes.
Therefore, you differentiate dt, this 1, 2, 3, fourth equation, dt square u is you div sigma. You differentiate in time, right?
Yeah.
And then also you put dtu equal w, for example. So you get two equations for
Yeah.
dtw and
Yeah.
w and u.
Yeah.
Right.
Okay, that's actually
okay.
great.
Maybe I will check a little bit of my ideas. Then
no, that's actually a good idea. I didn't consider that's okay. Yeah, as I said, you have a lot of knowledge that you someday
I will send you
we
very
should
quite
look at
old
these
papers,
equations.
right? to more than 30 years ago. But anyway.
Yeah.
Okay, so the idea is how to recover the derivative loss in the hyperbolic equations. Okay, anyway, so this is just how do
it's interesting. I find that it's so hard to couple these
quite hard.
Because and this was one of the points I wanted to make with this lecture series, that when you do this the steady state, everything fits beautifully.
Yeah.
There's absolutely nothing that's where you have to get your hands dirty. It just fits, right? But then for the time-dependent case, it's unless of course somebody has some nice idea.
I understand that you consider what to say, elastic equation, meaning is that the UTT plus Laplace square U is very good. I mean, usually.
Well, if you put that into your elastic equation,
known that the plate equations, but yes, I really understood that plate equation, mean of a plate equation is really nice for your argument. It's square U, yeah. No, I mean,
if you
dt
put this,
square
this
U
is a
minus,
non-damping.
This is also the damping, but
yeah.
No, okay.
Is this what you have, the term you have in the viscoelastic equations?
Yeah, viscoelastic equations. This dt square U just you used it. dt square U plus Laplace square U. And then some damping or dt Laplace U or something like that.
That's of course a damping term that you find a lot. Also just because the damping
not the Laplace square U, dt Laplace U.
dt Laplace U is also damping, yeah.
Not so much Laplace square U is more damp.
Yeah, that I think Laplace square U turns the whole, makes it completely elliptic.
Yes.
Or parabolic. So the hyperbolic becomes completely parabolic with this damping.
Yeah, you are. But anyway, you are very clever to do your final. Okay, so your final part of your talk is very clever ideas. So thanks very. By the way,
thank you so much.
But by the way, you can consider instead of gamma, just a periodic solution. Instead of a periodic solution, you consider R2. It's like the plate equations, the infinite plate.
Yeah. So I also wanted to do that.
Yeah. Then maybe I hope that you get some of the nice polynomial decay properties.
There is one big problem when you do if you do these time periodic solutions in the half space where you have where you have the plane, so you don't have any boundaries, but you have infinite domain, as you point out. There is the problem. Then you run into another problem, which is the decay of your solution at infinity. And if you look at the initial value problem, this is not a big problem. But if you look at the time periodic problem, they have terrible decay properties at infinity.
No, I don't talk about the parabolic. Periodic. Everything, not periodic. I mean, just U is defined as wave equation.
Okay. No. So the time you want to have the whole axis.
Yeah, because I'm not so aware of the parabolic.
Sure. Okay. Yeah. That's actually also. Okay. Actually, that's a good point. This what I can show here for the time periodic. One should be able to also show for initial value problem, parabolic initial value problem. similar kind of effects of the damping. That's actually a very good point.
Okay, anyway, there are a lot of quite nice problems on those questions.
Absolutely.
Yeah.
Thank you for listening.
Yeah.
Okay, I'll say goodbye.
Very nice
Bye.
lectures.
Thank you so
Maybe I
much.
will close it. Yeah. Thank you.
Bye.